Okay. All right, so already in section 10.4, we talked about the measure of central tendency that deals with the mean, median, and mode. Okay, so that was that. And then we went over how to choose the most appropriate measure of central tendency. Usually it depends upon the on the data itself. And also talked about measures of spread. We talked about basically the finding the range, which is the upper extreme, upper extreme minus the lower extreme. And also we talked about lower quartile, which is Q1, the upper quartile, which is Q3. The median is also Q2. Okay, and we talked about how to calculate the interquartile range, which is of course Q3 minus Q1. And then we use that 5-number summary, which is of course the lowest number, that's the minimum, Q1, Q2, Q3, and the maximum value to create what they call a box plot. Usually a box and whisker plot or a box plot is usually going to have the box that has Q1, Q2, and Q3. Your whiskers will consist of Q1 and the minimum and the maximum value. Okay, and we did an example of how to create a box plot that had an outlier in it. And of course, an outlier is usually going to be a value that is 1.5 times the interquartile range above the interquartile, or the upper quartile, or 1.5 times the interquartile range below. Okay, and usually outliers are indicated with an asterisk or a dot. Okay, so to pick up where we left off here, we're going to look at the mean absolute deviation, also the variance and the standard deviation of a set of numbers. All right, a measure of spread is needed when the data are summarized with a single number, such as the mean or the median. The simplest way is to find the range. We've already talked about how to calculate the range of a set of numbers. That's the highest data value minus the lowest data value. And we can also use the interquartile range, or the IQR, as well. Now, the most sophisticated measure of variation would be the standard deviation. Okay. So first of all, we're going to talk about the mean absolute deviation, and then we'll go into standard deviation. And also, we'll end this section with normal distributions, or the normal curve, and some applications to the normal curve, and percentiles. All right, in this case here, mean absolute deviation is going to be abbreviated MAD. That makes use of the absolute value to find the distance each data point is away from the mean. Then the mean of those distances is found to give what they call an average distance from the mean for each of the points. Okay, so in this blue box that you see in the middle is a definition of mean absolute deviation. Right above it is just a procedure of computing the mean absolute deviation of n numbers. When you want to measure the distance from the mean by subtracting the data value minus the mean. Okay, well, to begin with, you have to find out what the mean is. And that is, of course, X bar, which represents a mean. Okay, so that means you have to take the average of all of your numbers in that data set. And that's before you can subtract your data value minus the mean. And then second, you're going to find the absolute value of each difference. Keep in mind that the absolute value is always going to be a positive number. It's never going to be negative, because absolute value represents a distance a number is from 0 on the number line. And then you're going to add up those absolute values, which is going to be called the absolute deviation. And then for the mean absolute deviation, or MAD, you're going to divide that sum by the number of scores. Okay. So this is what the mean absolute deviation is defined as. Okay. So we use that procedure up here at the top to come up with our mean absolute deviation. And it's usually absolute value of x1 minus x bar plus the absolute value of x2 minus x bar plus and so on, all the way up to the absolute value of xn minus x bar. All that's divided by n. N is the number of data values that you have here. So in this example here, let's say we got 4.1, 7.1, 12.1, 5.1, and 2.1, and we want to find the mean and the mean absolute deviation, or MAD, of the data. Then we're going to round the final answer to one additional decimal place than the data. So as you can see, that data set is only to one decimal place. So when we round the final answers, it's going to be to 2 decimal places. Okay. All right. So now let's see how this works. So in this case, here we got 4.1. Let me put this as a table. X is going to be the data values here in this column. So I have 4.1, 7.1, 12.1, 5.1, and 2.1. No, not with the mean. Okay. So if I want to find out what x bar is, which is what the mean is, I just take the sum of these numbers, and I'm using this Greek letter sigma for the sum of the x's divided by n. That Greek letter right there is sigma, meaning the sum, in case you haven't seen that before. So we're going to add those 5 numbers together. That sum is 30.5 divided by n. In this case, there are 5 data values in this set. So if I do 30.5 divided by 5, I'll get how much? 6.1. So the mean of this data set is 6.1. The sum. Probably hard to see on this screen. That means the sum of, okay, let me use blue. That's what that Greek letter means. Sigma means the sum of the x's divided by n. So that mean is going to be 6.1. Now here's the next thing I'm going to do here. Measure the distance of the mean by subtracting the data value minus the mean. So here, this will be x minus x bar in this next column. So I'm going to take each data value minus this mean. And some of them will be negative, I can tell you that right now. So like if I have 4.1 minus 6.1, and I'll go ahead and write this out. 4.1 minus 6.1, that would end up being -2. And then 7.1 minus 6.1. 7.1 minus 6.1 will be 1. Then 12.1 minus a mean of 6.1. That will be 6. And then 5.1 minus 6.1, -1. And then finally 2.1 minus 6.1, -4. All right, so That's what x minus x bar will be for each of these data values here. And then we find the absolute value of each difference. So this next column would be the absolute value of x minus x bar. Absolute value of x minus x bar. So here we're going to take the absolute value of each of these differences here. And keep in mind, absolute value is going to be positive. So in this case, if I take the absolute value of -2, that's going to be 2. And the absolute value of 1 is just 1. Absolute value of 6 is 6, and the absolute value of -1 is 1, and absolute value of -4, that'll be 4. Okay. And then next, I'm going to, any questions? Questions? Okay. Next, I'm going to take the sum of these deviations. So those numbers that you see here, the 2, 1, 6, and 4, those are your deviations here. So if I do 2 plus 1 plus 6 plus 1 plus 4, that's going to be how much? 14. And then to find the mean absolute deviation, which is going to be MAD, that's going to be the sum of the deviations here divided by n. And the sum of the deviations was 14. The number of data values, which is n, that's going to be 5. So what is 14 divided by 5? 2.8. Okay. So that 2.8 represents the mean absolute deviation. Okay. So the mean absolute deviation of this data set would be 2.8. Okay. All right, any questions on that example on finding the mean absolute deviation? Okay. So basically all you're doing there is just following those 4 steps. And I don't know, on the handout, I kind of left off where you have to find the mean, which is the first thing you have to do there is find the average of that data set. And then subtract each data value minus the mean to get your deviations. Some will be positive, some will be negative. And then after that, you take the absolute value of those differences, sum these deviations together, and then divide by how many data values you have. Okay. All right, so much for finding the mean absolute deviation. All right, so now let's take this a little bit further. Finding the variance and the standard deviation. Now, these are the 2 commonly used statements of dispersion. Okay. As we already talked about range. Now we got variance and then we got standard deviation. Now, these measures are based on how far the scores are from the mean. Okay. Now, the way we compute the variance and the standard deviation is going to be as follows. So here we got 6 steps to do this. Number 1, you have to find the mean of the numbers. And again, you're going to add those data values up and divide by how many you have. Then number 2, you're going to subtract the mean from each number. So in other words, it's going to be the data value minus the mean. Some will be positive, some will be negative. And then number 3, you'll square each difference found in step number 2. And then number 4, you're going to find the sum of those squares in step number 3. Now in step number 5, you're going to divide the sum in step number 4 by n, which is the number of data values you have, to obtain your variance. Once you obtain the variance, then the standard deviation is going to be simple. All you have to do there is just take the square root of that variance. And that will give you the standard deviation. So here is that definition of the variance and standard deviation. Okay. The variance, you just go through these first 5 steps. And then once you find the variance, the standard deviation is nothing more than just the square root of that variance. Okay. And they have it written out as this, the square root of x1 minus x bar quantity squared plus x2 minus x bar quantity squared plus x3 minus x bar quantity squared, and so on, all the way to x of n minus x bar quantity squared. That whole thing is divided by n, and that whole quotient is underneath the square root symbol. Okay. All right, so now let's see if we can apply that procedure that's up here with this example. Here we have 7 students on an intramural team. They weigh 195 pounds, 202 pounds, 190 pounds, 201 pounds, 192 pounds, 211 pounds, and 188 pounds. What is the standard deviation of the weights of these students? Okay. Now, the way I'm going to do this, just like I did for the mean absolute deviation, I'm going to create a table just like this. So here, this will be x, which is the data, each data value. So we have 195, 202, 190, 201, 192, 211, 188. So the first thing we need to do is find the mean of these 7 data values. Okay, so of course x of x bar, that's the sum of the x's divided by n. So we first add 195 to 202 plus 190 plus 201 plus 192 plus 211 plus 188. This will be 1379. And I did say there's 7 data values here. So if I do 1379 divided by 7, okay. Oh, that's good, because we came up with a whole number for the mean. 197. For a moment there, I thought we were going to get a decimal value. So the mean of this data set would be 197. And then I'm going to subtract the mean from each number. So in this next column, I have x minus x bar. Each data value, we will subtract from it 197. So if I do 195 minus 197, I'll write this out. That's going to equal to what? -2. And then 202 minus 197, that'd be 5. So 190 minus 197, -7. And then 201 minus 197, that will be, and then 192 minus 197, -5. And then 211 minus 197, 14. And finally, 188 minus 197. 8 and 9. All right, so those are my differences for each number. Now, for each difference, this is step number 3. Square each difference found in step number 2. So in this column, this is going to be x minus x bar quantity squared. So that means I square each of these numbers. And keep in mind, anytime you square a negative, it's going to be positive. So if I square -2, this will be 4. If I square 5, that would be 25. Square the -7, it'll be 49 because that's -7 times -7. All right, square that 4, it will be 16. Square -5, it will be 25. Square 14, 196, and square -9, 81. All right, so now the next thing I'm going to do here is this step number 4, find the sum of the squares in step number 3. So this column will have to be squared. Okay. And I'm going to use that summation notation again, that sigma notation. That's the sum of x minus x bar quantity squared. So I add 4 to the 25 to 49 to 16 to 25 to 196 to 81. And what would that be? Yeah. So this will be 396 here. And then step number 5 is to divide the sum in step 4 by n, and that's to obtain the variance. So in other words, I'm going to move over here. That variance, of course, is just a sum of x minus x bar quantity squared divided by n. So the sum of the x minus x bar quantity squared, that's this number 396. Divided by n, that's the number of data values that we have, that's 7. Excuse me. So 396 divided by 7, yeah, to one decimal place, we'll say 56.6. So this right here is your variance for this data set. And now for step number 6 is just find the square root of the variance to obtain the standard deviation. So your standard deviation is just simply the square root of the variance. And our variance was 56.5. So if I take the square root of 56.5, and let's say the one, okay. Around. So if we take the square root of 56.6, what would we get? So one decimal place. Yeah, about approximately 7.5. So that standard deviation of this set of data would be 7.5. And what that really means here, that this data set has a spread of 7.5. It's 7.5 standard deviations from the mean. Okay. All right, any questions about finding the standard deviation, or the variance and the standard deviation of a data set? Okay, so pretty much we just had to follow these steps that were given on your handout. Okay, had to first find the mean, subtract the mean from each individual data value, you'll get these numbers here. Then you have to square those numbers to get this next set of numbers. That's the sum of the squares. Sum these squares up together, you'll get 396. And then divide that by the number of data values we have, which is of course 7. That would give you the variance. And then finally, take the square root of the variance to get your standard deviation. Okay. All right. All right, next we'll move on to normal distribution. Okay, because see, in this case, standard deviations have something to do with normal distributions, along with the mean as well. A distribution of data is a listing of all possible values of the data and how often they occur. A very important distribution is a normal distribution. The graphs of normal distributions are usually bell-shaped curves, which are called the normal curve. And it is a smooth bell-shaped curve that depicts frequency values distributed symmetrically about the mean. And the mean, median, and mode all have the same value. So usually it's going to be at the center of this of the curve. Okay, so here's where X bar is. That's the mean right there. It's usually at the center. And as you can see, it's going to be symmetric, meaning that the left side is the mirror image of the right side. Okay, so if I was to fold this paper along this line right here, the left side would lie on top of the right side. That's what we mean by symmetric. Okay. Now the curve extends infinitely in both directions and gets closer and closer to the x-axis, but it'll never reach it. So if you look at the ends of this normal curve, or what we call the tails in statistics, you'll see that it's going to get closer and closer to this x-axis right here, but it'll never touch the x-axis. Now, on a normal curve, notice that these numbers that you see here, the 68, 95, and 99.8%. Okay. Now, in statistics, we call that the empirical curve, or the empirical rule, I should say. So with a normal curve, about 68% of the values lie within one standard deviation of the mean. So here, to the left and to the right, got 34 and 34, add those together, you'll get 68%. So within one standard deviation of the mean, you'll have 68% of all of your data values. All right, and then next is about 95% lie within two standard deviations of the curve. So two standard deviations to the left and to the right. If you add 13.5%, 34%, 34%, and another 13.5%, that adds up to 95%. That represents two standard deviations of the mean. Okay. And also in statistics, when we're using 95%, we're dealing with what they call usual values. So the usual values will be between two standard deviations of the mean, will be within two standard deviations of the mean. And that's 95% of your data values. And then finally, 99.8% of your data values will be within three standard deviations. So here's three standard deviations to the left and to the right. Add these numbers together, you'll see that it's going to be 99.8%. Okay. And the 0.1% on the left and the 0.1% on the right, that when you add those together, that makes up 100%. So in this case, the area under the curve altogether represents 100%. So if you ever take statistics, you're going to see something, you're going to hear something like this about the empirical rule for a normal curve. All right, take a look at this example here. This is example 11. Now I'll leave this curve up here so that way you can see what's going on here. All right, fuel economy estimates for automobiles built in a certain year predicted a mean of 24.8 miles per gallon and a standard deviation of 6.2 miles per gallon for highway driving. Assume that a normal distribution can be applied. Within what range are 95% of the automobiles? So you're told a mean of 24.8 miles per gallon and a standard deviation, which I'm going to abbreviate as SD, of 6.2 miles per gallon. All right, now what I'm going to do here is draw a normal curve on the board. So here's my horizontal axis, and this will be the normal curve. It's like this. And X bar is usually going to be at the center of this curve. And then I'm going to draw 3 marks, which is going to be this. This first mark represents the mean plus 1 standard deviation, which I'm going to call S. And then if I go out another, this will be the mean plus another standard deviation, which is going to be X bar plus 2S. And this will be X bar plus 3S. Okay. That's 1 standard deviation, 2 standard deviations, 3 standard deviations above the mean. Then I'm going to go to the left. Or below the mean. So 1 standard deviation below the mean will be X bar minus 1S. Then if I go out another standard deviation, it'll be X bar minus 2S. Then 1 more off to the left will be X bar minus 3S. All right, now my X bar, which is the mean, that's given to be 24.8. So that X bar is 24.8. Now to come up with a standard deviation above that, now the standard deviation is 6.2, so I'm going to add 6.2 to the 24.8. So 1 standard deviation above 24.8 would be this number, 31. Okay, the mean is 24.8, the standard deviation is 6.2. 1 above that, just add 24.8. Well, add the 6.2 to the 24.8, you'll get that 31. And then to go out another standard deviation above that, add 31 to the 6.2. This will be 37.2. And then add a, to find out what X plus X bar plus 3 standard deviations. Well, if that's 37.2, I'll add another 6.2 to that. This will be 43.4. Okay. Now, let's find out what these values are to the left. Okay. So this is 24.8 and our standard deviation is 6.2. One standard deviation below that means I need to subtract 6.2 from 24.8. And this will be 18.6. And then for X bar minus 280, if that's 18.6, I'll subtract another 6.2. That's 12.4. And then finally, for 3 standard deviations below that, we'll subtract another 6.2. And this will be 6.2. All right. Now, it's these numbers that I have here in blue is what's going to help me answer that question. Okay. And it just say within what range are 95% of the automobiles? Within what range are 95% of the automobiles? Now, if you look back, you'll see that 95% has to lie within 2 standard deviations of the mean. That means 2 above, which is right here, and 2 below, which is right here. This represents 95% of the data values. So in this case here, what will be the range of values here that's going to represent 95%? Right. 12.4, that's 2 standard deviations below, and 37.2, that's 2 standard deviations above. That range represents 95% of the data values. So these two represent 95% of, let's say, all automobiles. I'll say for all autos. Okay. Any questions on example 11 and how that was done? Okay. All right, now let's look at this other example on the next page. When a standardized test was scored, there was a mean of 500 and a standard deviation of 100. Suppose that 10,000 students took the test and their scores had a bell-shaped distribution, making it possible to use a normal curve to approximate the distribution. So here we're going to answer parts A, B, C, and D. How many scored between 400 and 600? And then how many scored between 300 and 700? How many scored between 200 and 800? And how many scored above 800? So what I'm going to do is use that same normal curve that I have up here. Okay, so let me go back here. Let me erase these numbers here. And I'll go ahead and erase this part right here. All right, now in this case here, the mean was 500, standard deviation was 100. So in other words, my X bar, which is the mean, is going to be at the center. Well, let me go back and use that blue again. So the X bar is going to be 500. And since my standard deviation is 100, I'm going to add 100 to the right, and just keep adding 100 to the right. And then I'm going to keep subtracting 100 on the left. So 500 plus another 100 would be 600. Add another 100, you'll get, and then add another 100, 800. Now let's subtract 100 each time. 100 from 500 would be 100. Subtract another 100 would be 300, and subtract another 100, 200. Okay, so, and we're going to be using that that normal curve to help us determine how many scores are between 400 and 600. All right, so this is 400, and that's 600. What percentage represents one standard deviation within one standard deviation of the mean? 68. 68% of your data values are within one standard deviation of the mean. So that means here, if I take that 68%, and that's going to be up 10,000. 68% up 10,000, because there are 10,000 students that took the test, and 68% are within one standard deviation of the mean. So we need to evaluate 68% or 0.68 times 10,000. And what would that be? Okay. 6,800. So that means that 6,800 students are within one standard deviation of the mean. They scored between 400 and 600. And then, well, this is part A. Now, part B is this. How many scored between 300 and 700? Okay, now I'm going to use a different color here. Let's see. Here's 300, and this is going to be 700, which is right here. That boundary represents how many, what percent? 95%. Because that's within two standard deviations of the mean. So 95% of those scored between 300 and 700. So let's find 95% of 10,000. That'd be 9,500. So 9,500 scored between 300 and 700. Questions on part B? All right, now what about between 200 and 800? So this is 200. That's 800. That's 3 standard deviations within 3 standard deviations of the mean. What would be the percent for that? 99.8%. So that means let's see if I can get this down here. 99.8% of 10,000. So that's going to be 0.998 times 10,000, which is how much? 998 with, sorry, 9,980. You're right. That's over 10,000. So 9,980 scored between 200 and 800. Now, part D is this. How many scored above 800? So in other words, we're looking for this number right here, this range right here. That's the number that scored above 800. Now, if you looked at that table, it was what? Oh yeah, 0.01. That area represents how much?
0.
Okay, 0.1%. Because the one on the left represents 0.2. I mean 0.1 as well. All right. So we got to do 0.01%. I mean 0.1% of 10,000. 0.1% as a decimal would be 0.001. And of means I have to multiply 10,000. So what would that number be? 10. So that means only 10 students scored above 800. And how many scored below 200? Just this space right here. How many scored below 200? Also 10, because if that's 0.1%, right here is also 0.1% as well. And 0.1% of 10,000, of course, is 10. All right, questions on the normal distribution and how to deal with what they call the empirical rule in statistics for the number of standard deviations. Okay, now here's some applications of the normal curve. Applications of the normal curve. Now let's say that a group of 200 students ask their teacher to grade on the curve. Okay. So when someone asks you to, when you're asking your instructor to grade, give a grade on the curve, this is what they're talking about right here. What that means here is this: they have to take the average of all the scores of all the grades of those students, and then use that normal curve. They have to look at the mean and the standard deviation to do this. So let's say the mean on a test was 71 with a standard deviation of 7. The graph shows how the grades could be assigned. Okay. So here is what that normal curve looks like. The mean is 71, so that means 71 is at the center. And then, of course, 68% are going to be within one standard deviation of the mean. So if I subtract 7 from 71, that will be 64. And if I add 7 to 71, that would be 78. And then next would be 2 standard deviations from the mean. Okay. Subtract another 7 from 64, you'll get 57. Add another 7 to the 78, you'll get 85. Okay. And the way this works is this: 68% that fall within one standard deviation of that mean would get a C. 13.5% that are below, that's within 1 to 2 standard deviations below that mean would get a D, and anybody less than 2 standard deviations of the mean would end up getting an F. Now, on the other hand, if you're within 1 to 2 standard deviations of the mean, above the mean, you'll get a B, and those who are 2.5%, meaning if you're 2 standard deviations above, you'll get an A. Okay. Now, based on that normal curve, the table shows that range that you'll see on the next page. So in this case here, if you get 85 or above, it would be an A. 78 to 84 would be a B. 64 to 77 would be a C. 57 to 63 would be a D, and anything less than 57 would be an F. And of course, if 2.5% of 200 students in the class, I think it's, 200. 2.5% of 200 would mean that 5 students will only get an A. Then 13.5% of 200 would be 27 for a B and 27 for a D. That means 27 students will end up getting a B, or 27, and also 27 students will get a D. And I also should include, since this is 2.5%, 2.5% of 200 would be 5. Only 5 will fail the course. 68% would be 136. That's 68% of 200, meaning 136 students would get a C in that class. So this is what grading on a curve means. Same holds true if it was the average of all the students in that class at the end of the semester, their grades at the end of the class, end of the semester. Okay. Sometimes it might be helpful, sometimes it won't. Okay, just saying. All right, next we'll talk about percentiles. And that'll be the last thing in this section I'll discuss, percentiles. Okay. When students take a standardized test such as the ACT or the SAT, their scores are often reported in percentiles. And what a percentile is, it shows the person's score relative to other scores. In other words, usually when you see test scores like, and then they have a percentile, like let's say the 83rd percentile, what that really means is this. If you were to look at, let's say 100 students all across the country, you've outscored 80, you've done better than 83 of those students, or 83% of those students that took that test did worse than you. And here percentiles are divided into 100 equal parts, and deciles are points that divide the distribution into 10 equally spaced sections. I don't think we ever use deciles when we're dealing with in real life, or when you're dealing with test scores. The R percentile is going to be represented by a piece of R. So let's say in this case right here, in a class of 65 students, Heather has a rank of 12. At what percentile is she? There's 65 students in the class, and Heather is ranked number 12. What percentile is she? So, in this case, all right, we have a class of 65 students, and her rank is 12. So that means we need to find out how many students were ranked below Heather. So if Heather is ranked number 12, let's subtract 12 from the 65 students in that class. So 65 minus 12 would be 53. That means 53 students had a rank lower than Heather. And to find that percentile, I'm going to take this 53, divide that by the 65, and I'm going to multiply that by 100. Okay. Let's round to the nearest whole number, 82. So that means that Heather is in the 82nd percentile. What that means here is 82% of those students in that class ranked lower than Heather. Okay. All right, any questions about calculating a percentile? Because here, if we have 65 students, we have to find out how many were lower than 12. So we have to subtract 12 from 65, you get 53. And then take that 53 and divide that by the number of students and then multiply by 100. Okay. All right, so that ends section 10.4 dealing with measures of central tendency and variation.